Okay, everyone, let's get started. Okay, so we've got Lab 3 was originally due on Sunday, and then last week I extended it to Wednesday, but then Charles reminded me that if it's due on Wednesday, that's basically allows the Wednesday lab section to work on it in lab, and then the Thursday to not. So I extended it again silently to Thursday, this Thursday. So Lab 3 is due this Thursday. It looks like everyone took exam 1. At 49 students take it. The average score was 80.3%. The grade distribution is here, a little hard to read because I got this from, I got the distribution from Moodle. But we had 13 A's, 20 B's, 5 C's, 7 D's, and 2 F's. So that looks good. And then for each question, I'll go over the questions briefly here. If you have any questions, let me know. But for each question, I marked the percentage of the students who got the question right. So question 1 was 73% of you got this correct. The question was, consider the following module. Which of the following waveforms could be generated from this module? And this module basically takes an input, which is A, and it delays it by 1, 2, 3 cycles to become B. So B is A, but delayed 3 cycles. So if you look at these waveforms, they're actually all the same except for B. So you can see that B, in this one, B starts out as a 1. In this one, B starts out as an unknown value for 1 cycle. Here it's unknown for 2 cycles, and here it's unknown for 3 cycles. So, so the question is, how many cycles should B be unknown for? Well, if B is the 3-cycle delay version of A, then it'll be undefined for 2 cycles, right? And so you can see that, like if you go to this waveform, so this waveform is the one where B is undefined for 2 cycles. I don't know how well you can see these labels, but this clock is on the top, then you've got A, B, B delay 1, B delay 2. So, A is, it looks like this. It's high for a cycle, then low for 2 cycles, then high for the rest of the time. And so B delay 1 should be basically that same signal, but shifted by 1 cycle. Now this is a little confusing because B delay 1 gets a value, has a value right at the beginning, but if you look at the shape of it, it's high for, in this case, 2 cycles, low for 2, and then high again. So if you compare B delay 1 to A, it's shifted by 1 cycle to the right. And then likewise, B delay 2 is also shifted, is the shifted version of B delay 1. You see that? So B delay 2 is the same as this guy, but shifted 1 cycle to the right. And then finally, B should be just one additional cycle of delay relative to B delay 2, right? Does that make sense? So the answer is this one. So you're looking for, basically you're looking for, probably the way I would have approached this is I would have looked at A, and then from A you want to look at B delay 1 and make sure it's delayed by 1 cycle. And then B delay 2 should be delayed with respect to B delay 1, and then B should be a delayed form of B delay 2. Now, these are deliberately out of order. The statements in this always statement are out of order. You would expect them to start with this one, right? But it doesn't. The order doesn't matter because they're non-blocking assignment statements. Okay. So I actually expected this to be lower because you're looking at the subtle difference between waveforms, but you all did well on this. Question 2, the following system Verilog code will generate a repeating sequence of n values in consecutive cycles. What is the value of n values in n consecutive cycles. So basically the idea is that how many values will come out, be generated, and then be repeated over and over again. So this one was harder than the first one. Only 61% of you got this correct. And so I did not put the answers on here so to figure this out. Okay, so when we reset, we start out with state. State's a 3-bit signal, and it gets initialized as 0, 0, 1. And then on the next cycle, it's going to become, well, basically it's just going to shift 1 bit to the right. You see that? So state 0 goes away, it gets shifted off the right-hand side. We have state 2 and state 1. So that 1 goes away, and that 0, 0 shift down. Right? And then the most significant bit then becomes the XOR of state 2, 1, and 0, the old state 2, 1, and 0. So you got to go up. So what is the XOR of, the 3-input XOR of 0, 0, 1 would just be 1, right? Because XOR is a modulo 2 operation, right? And then in the next cycle, we're going to take the 1, 0, those will get shifted down. And again, we'll do an XOR, which will be 1, right? Because 1, 0, 0. If we XOR at 1, 0, 0 together in a 3-input XOR, we'll get 1. And then the next cycle we'll take, that 1, 1 will shift down, and the XOR of 1, 1, 0 is 0, because that's, there's two 1-bit set. I'm not seeing a repeat yet. Okay, so then we take 0, 1 and shift that down, and shift in a 0. Right, because there's 2 bits set. Okay, we might be seeing a repeat now. Looks like it. Okay, so now 0, 0, and then 1. Okay, so I think that's about the repeat now. Okay, yeah. So it looks like there's basically 4 values that repeat endlessly, right? So that's the answer to that question, 4. So to solve it, you pretty much just have to, figure out what comes out in each cycle. Yes?
Well, this kind of 3-bit thing, it can be maximum of 6 values as an n. Like, because 2 to the third minus 1, it would be actually 7 maximum.
Mm-hmm.
Yeah, thank you.
Well, there's 7 possible, but I don't know if that's the longest period. I'm not sure. Well, this is called a linear feedback shift register, by the way, and this is one way to generate pseudo-random sequences of numbers. This actually, the value that you put in the most significant bit can be defined as a polynomial, and different ways. There's different ways to do that. That will give you longer sequences before they start to repeat. Ideally, you'll never repeat. Like ideally, we should be able to generate a random sequence of values that just never repeats. It's an endless sequence with no pattern, right? But that's not how these work.
But does it constantly change the way which bits are XORed?
Right. Well, yeah, that's what I'm saying, is that, you can use different bits to XOR and get different sequences with different periods, but ideally the period would be infinite. I don't know if that's even possible, though, with these things. I think there's always a period. I think that's true even if you go into Linux and you call rand. I think there is a period. This is very, very, very long period. That's what you want. But this is a very short period, so this is not a very good random number generator, obviously. Okay, next question. 49% got this one right. Which of the following statements is false? Non-blocking assignment statements can be used inside an always calm block. That's true. You can do that. That's not the convention. Conventionally, you would not use you would use blocking statements inside always calm, but you can use non-blocking. That's up to you. System Verilog allows the designer to mix structural HDL and behavioral HDL in the same module. Yeah, well, that's actually There's no problem with that. Some people may not want to do that because they're, you know, they're purists that want to have one or the other, right? But you can do that. Multiple always blocks can read the same input signal. Sure, no problem there. You can't drive the same output signal, right? That would be a contention or conflict. System Verilog modules are the way in which hierarchy, abstraction, and regularity are applied to logic design. Yes, true. Always blocks cannot be used to design combinational logic. Of course they can, yep. If statements cannot be used outside of an always block. True, right? So wait, which one is false? It's E. Always blocks cannot be used to design combinational logic. Yes, sorry, yes, I had that. See, I got it backwards in my head. Because you're asking to, you're looking for the one that's false. You know, I'm used to, you know, it's more intuitive to look for the one that's true. But yeah, you're right. E is false, right? Yeah, you can design combinational logic with an always block. Yes?
What about having always comp?
Sorry?
But what about having always comp? Always comp is the always, but it simulates combinational logic.
Yes, yeah, I was just in general always blocks. Always com, by the way, is always com is just an always block, but it's you're giving the compiler a hint as like if you use always com, all that is an always at star that says I'm just making an always block and you're giving the compiler a hint as to what your intentions are. Right? That's all it is, but at its heart it's just an always block, right? It's just designed to prevent bugs, essentially.
Yeah, but it is always blocked where we simulate combinational logic.
Mm-hmm. Yeah.
Why is false then?
Oh, it's false because, and this is what tripped me up too. It's false because the statement said always blocks cannot. Yeah, that was the part. I got tripped up by that just now too. Yeah, that was a little. That's probably why only 49, less than half of this class got that right. It was the cannot. That was the part. It's tricky. So that makes it false. This one, 78% of you got it right. Which of the following is not a problem? Again, this is another question. I need to stop asking these. What is not a problem? Assigned statements are improperly used within an always block. That's a problem. Yeah, that is a problem. So that's not the answer, because that is a legit problem. The assigned statements have 4 bits on the left-hand side and 3 bits on the right-hand side. That's a problem. There is no structural HDL. That's not a problem. Yeah, that's fine. You don't have to have structural HDL. You can have just purely behavioral, and that's what that is. Yeah, I might have used it in the review. Yeah, okay, well, good. That's probably why so many people. But then again, I mean, you would think that 100% would have got it right since I pretty much gave the answer in the review.
It's a noise in the system.
Yeah, oh yeah, it could be. To what value will the following system Verilog code be set to signal B when A equals 0, 1, 0, 0? I think I might have talked about this one in the review too. It's going to be 0, 0, 0, 0, right? Because you're going to take the low order 2 bits, swap their order, right? Right, because this is A0, that's A1, and then 2 copies of that, right? So 0, 0, 0, 0. 2 copies of A2, of course, which is the leftmost bit. Which of the following system Verilog statements will receive 3 1-bit inputs, A, B, and C, and produce a 1-bit output Y that's true if an odd number of its inputs are true? Yeah, this is basically similar to that. Yeah, it's going to be A. Yeah, the XOR. Assume the following Verilog module. How many total bits comprise the inputs? 2, right? Just A and B. Yeah. Oh no, sorry. Fill in the missing. Wait, it doesn't say that, does it? Oh yeah. Yeah, sorry. Fill in the missing values from top to bottom for the test vectors. 100% of you got this right, which is great. So pretty much it's just a truth table. So this is a question that you really only need your your material from 212 to be able to answer. Sorry, 211 rather. So this is not A and B. So not A and B. So this row would be a 1, and the other rows would be 0. Right. So the second row down would be 1. Which of the following system Verilog statements takes as input an 8-bit value and produces an 8-bit output value where the upper 4 bits and the 4 bits of the input are where the upper 4 bits and the 4 bits of the input are swapped? Upper 4 bits and 4 bits of the input are swapped. I guess that's a typo, but yeah, 96% of you got this right, and so we're swapping E. Yeah, we're swapping the upper and lower 4 bits of the input. Yes.
I think the question depends on how you define the input. It's 7 to 0 or 0 to 7. Because if it says 7 to 0, then answer is E. But if it's 0 to 7, this would probably be 7 to 4 and then 3 to 0 or something like that. Well, 0 to 4 and 5 to 7.
That's a good question. So you're saying if you declared it from as 0 to 7.
Yeah.
I don't know if that would actually work or not. Have you ever tried that?
No.
So I always assumed that the reason why Verilog had you define both ends of the range of a vector was because you could define it backwards, and then if you assign that value, you'd be effectively swapping the bits. But it doesn't work that way. I've never seen any difference at all from reversing, like as doing 7 down to 0 as opposed to 0 up to 7. I've never seen it compile any differently.
Big endian and little endian. What to define as most significant bit? What to define as only?
I don't know if it does that. That's how I expected it to work, but I don't know if it actually implements that. I tried it once because I remember I was putting a slide together for class and I was going to try to show that, and the compiler just ignored it. It just treated it as if I had put it in the traditional way. So I'd have to try that. I don't know. But in this, the question though is pertaining to the material that I presented. But I'm not sure. I'd have to try that. I don't even know if that's true or not. Okay. Which RISC-V instruction will multiply the value stored in register 4 by 4? Okay, so this one. 88% of you got it right, so everyone did well. But the idea behind this question is that this is highlighting a difference between RISC-V and MIPS. If it were MIPS, it would be 4. If it were MIPS, you would use SLL x4, x4, 2, right? So that would multiply the value in x4 by 4 because it's 2 to the second power, right? And we're shifting left. So shift left multiplies, and you're multiplying by 2 to the power of the shift amount, right? However, that doesn't work in RISC-V because in RISC-V you have to use the SLLI to do that, right? So the answer is B. If you were remembering your MIPS, you might have chose E, right? Yes?
What is SLA? SLA.
I don't know, something I made up. Made up instruction. I don't know. Shift left arithmetic, I guess, but nothing that doesn't exist. Suppose you wish to design a system Verilog module which accepted 5 input values of 8 bits each and produced as outputs a single 8-bit signal being a copy of one of the 5 input signals selected by n. Oh yeah, I remember that. This is Charles's question. So this is basically the way that it's worded. If you read it, it's defining what a mux does. And so the question is, what is the minimum value of n? In other words, how big is the select input need to be in order to select 5 input values? What would be the log base 2 of 5 rounded up, which would be 3. Yeah, because 3 would give you up to 8 inputs, right? 2, if you had a 2-bit select, you'd only be able to support 4 inputs, but there's 5 here. Okay, assume a CPU design below has a bug where the wire labeled ALU source EX could only be driven to the value of 0. So this question is basically saying, say there's a defect in the design somehow. There was a problem during the manufacturing process. Piece of dust, got put down during the photolithography process, and essentially the ALU source EX, which is ALU source, this guy, it's stuck at 0. So that means that whatever comes in the one input would never go through, right? You'd never be able to send in the sign extended. You'd only be able to send in the contents of the RS2 register, right? So which of the following instructions would no longer execute? Well, basically anything that requires the ALU to get the contents, or the immediate, right? The sign extended immediate. Well, the LUI does have an immediate, but that instruction doesn't use the ALU at all. It actually uses this mux, because the LUI uses this data path that bypasses the ALU entirely. So this one is a little bit, that's confusing, because that has an immediate, but it doesn't use that data path into the ALU. Neither does the CSRRW instruction, and of course the MOL-H and the SLL would both just use this wire, right? So the only instruction that uses this secondary wire, or this secondary data path from the sign extended immediate into the ALU, would be the ADI. So the answer is C. So basically, if that wire were cut, or hardwired to 0, everything would work except that one instruction, or any instruction that uses the immediate. Okay, when the program is being executed on a 3-stage RISC-V CPU, in which stage is the 4th instruction fetched when the 2nd fetched instruction is in write back? Okay. So the 2nd instruction is in write back. The 4th instruction fetched would be 2 cycles behind it, right? Which means fetch, right? Yep. And then the 3rd instruction fetch would be an execute. So it would be fetch. Consider the RISC-V microarchitecture shown below. Oh, how many of you got 94%? Okay, wow, that was an easy one. Consider the RISC-V microarchitecture shown below. What is the value of reg-write-ex, rd-ex, reg-select-ex when the following instructions are in the corresponding pipeline stages? X signifies I don't care. Okay, so all 3 of these are execute stage, so we only care about the instruction that's in execute, which is the LUI. And so reg-write-ex would be 1, right? Because LUI writes to a register. So I need to write this down, otherwise I'll mess this up. Okay, so first bit is a 1, right? Going from left to right, most significant to least significant. RDEX, which is RDEX. Yes, RDEX, that's the register, the destination register. Yeah, sorry, RDEX. I had to think about that. Okay, so what is the destination register of the instruction in the EX? Well, that would be 5, right? Because we're writing to 5. So 5 would be, in 5 bits, would be 0, 1, 0, 1. No, sorry, 0, 0, 1, 0, 1, right? 1, 2, 3, 4, 5. 5 bits. So this is 5 bits with the value of 5. 0, 0, 1, 0, 1. Reg select. Okay, again, it's referring to the LUI. So the reg select should be, reg select, where is that? Reg select is here. That's determining what actually gets written. So because it's the LUI, we're going to choose input number 1 because that's the immediate value, right? So that should be 1, but it's 2 bits. So that should be a 0, 1, right? Okay, so if we divide this into, I don't remember how the answers were set up, but one way to show this would be 1, 2, 3, 4, 5, 6, 7, 8. 8 apostrophe B 1, 0, 0, 1, 0, 1, 0, 1, or 8 apostrophe hex, which would be 9, 5, I guess. Right? And I don't know what it is in decimal. I think it was the hex, though, was the answer. Okay, and then last question. 57%, so this was a tough one. Consider the RISC-V microarchitecture shown below and assume the following instructions in the corresponding pipeline. Which statement is true? Now this one, see now it says which statement is true. Now we're looking for the true statement. The register file is bypassing the register on read port 2. Okay, now for that to be true, you have to look at what's in write back and what's in EX, decode EX, right? Now notice I put decode EX. I think the reason I put that there was I wanted to emphasize the fact that this is also the stage where you're reading the registers, and this is, and obviously write back, you're writing a register. So if you're writing a register that you're also reading in the previous instruction, then you've got a bypass. But that's not happening because the LUI doesn't read any registers at all, although technically it is, because it's still going to be reading registers. Whatever the RS1 and RS2 registers are inside the machine language version of that instruction are going to get read, but they're going to be discarded. But technically that could still activate the bypass path. I didn't think of that actually when I wrote the question, but I doubt that's unlikely to be happening. Yes?
Question, how that it might activate bypass and not bypass?
Because we're writing back 3.
Yes.
So if the RS1 or the RS2 field inside of this instruction just happened to be 3, actually in this case it would have to be RS2, right? So if you took the RS2 field, I don't even, see with RISC-V, I don't even know what that bit field is. I don't have it memorized. I used to know that for MIPS. It was 20 down to 16, I think, but whatever it is, I'd have to go back and look at the encodings. But whatever the field is for RS2, if that just happened to match 3 for this instruction, for the, I guess the LUI instruction, right? Then the bypass would be activated even though it wouldn't have any effect on anything, right? But I'm going to assume that one's not right. B, reg select EX is set to 0, 0. So that would mean the instruction in EX, which is the LUI, it would be selecting 0, and of course that's not going to be that's not true. Now you might say, wait a second, you're looking at reg select WB. Yeah, I know, but the question is, when this instruction does get to the write back stage, what is it going to be selecting? Well, it's going to be 1, not 0, right? So that's not true. C is the value of read address 1 is 3. Okay, now this one's tricky because I'm asking about read address, but you might be like, what stage? Well, I didn't say that because the read address 1 is named that inside the register file. Outside the register file, it probably has an underscore EX on it, right? The signal name. But basically what I'm saying is the data, the first register we're reading is 3, which would of course again correspond to this LUI. And again, I don't think so. I don't think so. And then D is the value of register 5 will be 1, 2, 3, 4, 5, 0, 0, 0, 0 when the mul H instruction is in the WB stage. Well, basically what that means is that when that's true, that basically what that means is in 2 cycles. 2 cycles in the future, when this guy has moved down to WB, at that point that LUI instruction will have been written back and retired. And so the value that you write in the register 5 will have been the load upper immediate, which is 1, 2, 3, 4, 5, 0, 0, 0, 0, right? So that's the one, D. Okay, so yeah, I gotta, anyway, everyone yes?
How do we know which port, like for A we have read on a register on read port 2. How do we know which port we are reading from?
The read address 1 has to be the RS1 because the ALU is, well, you could probably reverse them, but you'd have to change the ALU because the ALU is expecting, like for example, when you do a shift, right, a shift instruction, it's going to take the input on the A input on the ALU and shift it by the amount on B, right? So if you swapped read address 1 and 2, there'd be implications in the design. You'd have to change stuff in the ALU, and I'm not sure. You'd have to put the ALU mux on port A. It would be complicated, right? I don't know why you'd do that. It just makes sense that read address 1 and thus read data 1 is tied into RS1, right? So the numbering is consistent, right? That's the assumption.
It wasn't explicitly said
Well, yeah, I don't know how much I talked about that in lecture, but in the design we gave you in the lab, that's the way it's set up. They're called read address 1, read address 2, and the presumption is that's how you have it hooked up. And we also gave you the ALU, so the ALU and the register file are designed a certain way. So this is assuming, this answer is assuming that you've been working through the labs. Okay, so there we go. That's it for the exam. Any questions? I was happy with the scores. I think that went pretty well. I think this might be the first exam I've ever given when there was no questions. No one asked any questions while they're taking the exam. So, and there were no typos or bugs or anything. There was a typo actually that I noticed just now in that one, the question where I swapped the bits, but evidently you guys, yeah, this one is worded strangely, but 96% of you got it right, so it wasn't an issue. Okay, so now we have to finish the microarchitecture lecture. I don't think this will take long. So the lab, as you guys I'm sure have noticed, there's a big effort that you have to put in to get lab 3 to work, right? That's basically all of the stuff you need to get the basic instruction set working. In the next lab, all you need to do is implement branches and jumps, and as it turns out, adding that functionality to your CPU design is really not a big deal. So in other words, what I'm trying to say is lab 4 should not be as much work as lab 3 was. Also, as far as the software part of the lab, you don't have to write any new software for this one. You're going to be taking your binary to decimal conversion code and your square root code and combining it. You have to add a little bit of code in there to combine it together and to deal with the fixed point decimal numbers that come out the other side. But basically there's very little software involved. And in terms of the hardware, you just have to add a few data paths in order to implement branches and jumps. So today I'm going to finish up the microarchitecture lecture. The last thing I'm going to present is how to do that. And then we'll be assigning lab 4 this week, right? Ideally we'd had it out today, but you still have till Thursday to do lab 3, yeah. So, okay, so what do we need to do to get branches and jumps to work? Okay, so I mentioned last time that branches use PC relative addressing. So when you have a branch in your assembly code, branches just branch to a label in your code. So you don't really think about branch addressing when you write assembly code. You just say branch to foo, and then you say foo : right, done. But in the machine code, in order to address foo, the address of that label, which is an address of an instruction that you want to branch to, is converted into a PC relative address, which is basically how many instructions up or down you have to go to get to foo relative to some reference point in your code, right? Now, what is the reference point? It's different in MIPS and RISC-V. In MIPS, the reference was the instruction that you would go to if you didn't take the branch. So the instruction that appears after the branch in the code, that's basically offset 0, meaning if your branch offset were 0 and you took the branch, you'd go to the instruction that you would have gone to if you hadn't taken the branch. Sometimes that's called the fall through position. Sometimes that's called the branch delay slot, and sometimes it's called PC +4. Right? RISC changed that though. In RISC-V, the branch target is relative to the actual branch instruction itself, meaning that in RISC-V, if your branch offset were 0 and you take the branch, it just branches to itself endlessly. And I show that here. I'm showing RISC. This is RARS versus MARS. Same instruction, branch if equal T1, T2 to foo, where foo points back to the branch. And you can see that the offset is 0 in RARS and it's -1 in MARS. There's another difference though. In MIPS, the branch offset was multiples of 4 bytes, meaning that a branch offset of 1 would skip ahead one instruction, would skip the next instruction if the branch were taken, right? In RISC-V, the branch offsets are multiples of 16 bits. And they do that to support their 16-bit instruction set, right? So in other words, when you're calculating the branch target, you take the offset and you multiply it by 2, whereas in MIPS you had to multiply it by 4, right? But in our case, we have a word address instruction memory, so we have a bit of an issue that we have to deal with there, because in our case we're not addressing our instructions by bytes but by words. Yes?
So MIPS instruction set is 4 bytes and RISC-V is 2 bytes, right?
So the RISC-V instructions, the normal instructions, let's see, how do I say this? Most RISC instructions that we're looking, or all the RISC instructions that we're studying are 32 bits. RISC-V has the ability to support longer than 32-bit instructions, believe it or not. I've never seen anyone use that. I've never seen that deployed anywhere. But the instruction set was designed to support wider instructions. It's also designed to have a 16-bit version too, where each instruction is only 16 bits. They did that as a way to reproduce that functionality that ARM has. ARM has the same ability, right? MIPS never had that though. MIPS never had a 16-bit instruction set. Now you might say, why would we ever use 16-bit instructions? Well, it was designed for really lightweight processors, right? Like something that you'd use in a wearable, like a Fitbit, that you want to use really low power consumption, really small memories. I've never seen anyone use it, not with ARM and not with RISC-V. But then again, I've never worked in industry, so maybe I'm naive. But
the reason why I'm asking is to jump one instruction before or after. We need to subtract or add the number of how many bytes our instruction is.
Right, so what I'm saying is that if you want to, in RISC-V, if your branch offset is 1, if you're using 32 bits, that'll crash your program. If the branch offset is 2, and you take the branch, then it will go to the next instruction, right? Because 2 will become 4. I know it's confusing. Let me show you what I mean by that. I have the code in here. Okay, so okay, so so the branch has an immediate. So there's an immediate field.
Without 0.
Yeah, wait a minute. Let me make sure yeah, here we go. Sorry. Okay, right. So basically the idea is you're taking the PC, the current PC, and notice it's PCEX. PCEX didn't exist in your old CPU. You have to add this signal. It's the 1-cycle delayed version of PC fetch, right? So now we have a PCEX. That just means it's the address of the instruction in the EX stage, right? And you still have PC fetch, which is the address of the instruction that would come after that, right, in the code. You're going to add the sign extended version of the immediate shifted by 1 bit to the left, which means multiplied by 2. The problem is that immediate is now goofed up in the instruction. Because if you look at the instruction, they've got the immediate is in 2 fields, 2 separate fields, and I have no idea why they did this, but the immediate is spanning the bits 12 down to 0. So the actual immediate as a byte address is a 13-bit immediate. However, if you look in the instruction, you see that there's no immediate bit 0 defined. So immediate bit 0 is assumed to be 0, and it's not actually encoded in the instruction. So all we have in the instruction is immediate 12 down to 1, right, which basically is a way for us to multiply that immediate by 2, right, because it's assumed that you're adding a 0 to that, right? And not only that, but bit 12 is over on the most significant bit of the instruction. Bit 11 is the least significant bit of this immediate field, and then you go back to this to pick up bits 10 down to 5, and back to here to pick up bits 4 down to 1. I don't know why. It's like a scavenger hunt to find all the bits of the immediate, right? So to try to make this easier on you guys, I figured this out. I think I figured this out. We didn't have any issues last semester with this, so I assume this is correct. So there's a line of Verilog code I give you called assign branch offset EX, which essentially just grabs those bits and does bit twiddling to figure out what the full 13-bit byte addressed immediate would be, right? And I say byte addressed because I'm including that extra 0, right? However, when you then use this for your program counter, notice that I take this branch offset EX. Oh, why is there no, is that a, hold on, sorry. I don't know why that should say branch offset EX to be consistent here. Okay, branch offset EX. So this is the byte addressed branch offset, and I shave off bits 1 down to 0, meaning that even though I multiply it effectively by 2 here, I then divide it by 4 here because your PC is word addressed, right? Now you might say, why do you have to go through all that trouble? You have to multiply it by 2 and then divide it by 4. Well, this is not a big deal hardware-wise, right? The compiler will, optimize all this stuff. But the reason why we have to use the same convention as RISC is because the branch offsets are calculated by RARs. So RARs is going to assume, like when you say foo colon in RARs and it calculates the branch offset, it's going to calculate that as a byte address, right, and encode it that way. So then when your hardware has to decode it the way that RARs encoded it, but then you can make internal corrections to compensate for the fact that you have a word addressed instruction memory, right? So that's what's happening here. I know it's kind of convoluted, but that's why we just gave you the code. Hopefully that'll make it a little easier. I also put these 2 tables here to try to show how you map the instruction bits to the offsets. Now, by the way, if you use Charles's idea and you have that decoder in there that basically takes the fields out of each instruction coding and names it, then it would be easier. You wouldn't have to grab them from instruction EX, right? Yes.
Branch address execute signal is 12-bit wide. That is why we have this additional branch offset execute 12 for sign extern.
Yes. Good point. Thank you. I didn't notice that here. I forgot. Yeah, I added it. There's 2 bits. There's 2 12s. Because the RISC instruction gives you 13 bits, right? But then we have to knock off 2 bits to divide by 4. So we only actually have an 11-bit effect. For our CPU, we have an effective 11-bit offset in the instruction. But you guys have a 4096 entry instruction RAM. So then we have to add an extra bit. We need 12 instruction bits. Our PCEX is 12 bits, and we want to add a 12-bit signal. And as a result, I added an extra 12 here. Yes, thank you. Thank you for pointing that out. Yeah, so there's a 12 here, and there's a 12 here. This is a sign extend that I'm doing. Yeah.
So the maximum size of the program this person can execute is 2 to the 12?
Yeah, instructions. Yeah, or 2 to the 14 bytes. Yeah, which is 16 kilobytes. I mean, you can put a bigger one. Actually, when we made that decision, we were using the old FPGA boards that were a smaller FPGA. You can extend your instruction memory if you want. None of the programs we write in the class are going to fill it anyway. Okay, so that was branch. Now we have jump. We have a J-type. I was so hoping that RISC-V would do away with the J-type instruction, the J-type format, because I always thought it was superfluous in MIPS, but they kept it, and they made it even more confusing. So in MIPS, as you remember, there was a J-type, and there was no register defined in the J-type at all. It was just opcode, 6-bit opcode, and a 26-bit offset, which was a pseudo-direct address. However, the J-type in RISC-V has a RD field, and thus it only has 6 plus 5 is 11, 32 minus 11. 21-bit? Yeah, there's a 21-bit immediate. Or no, I'm sorry, the opcode is 7 bits now, sorry. Again, MIPS was 6-bit opcode. We have a 7-bit opcode, right? Is that right? 7 bits, right? Yeah, 7-bit opcode, 5-bit register. So that's 12 bits. 32 minus 12 is 20 bits. Now the immediate is actually still 21 bits because it's 20. But remember that, again, we only go down to bit 1. We don't go to bit 0. So it's 20 down to 1.
A fairy tale of strange design decision.
Yeah, I know. I agree. I don't know why. So again, it's a 20-bit immediate, but it represents a 21-bit byte offset. But all of this is moot because we only have a 12-bit program counter, so we can put the whole program counter inside the J-type and still have bits left over because we have such a small instruction memory. So again, all you have to do is worry about how to map the bits from the immediate, which are again scrambled for some reason, into the the 12-bit program counter, which I do for you here. Okay. Now also notice that I add this to, so I calculate the offset and add it to the PC. You might remember MIPS didn't do that. MIPS used a pseudo-direct address in the J-type. The idea was that in the J-type you did not add the J-type offset to the PC in MIPS, but you still add it, so it's kind of like a branch in that sense, but you get more bits. You get more offset bits with a jump. So that's the main that's one difference between branch and jumps. The other is that branches are conditional and jumps are unconditional, right? Okay, yeah, sorry about that. There is a jump register instruction. This one, oh, by the way, the jump, the reason why we have that RD is that's our link register, right? So in MIPS, there was a jump, and then there was a jump and link. The jump and link would write to register 31, right? Always 31. But in RISC, they got rid of the jump. Now they just have jump and link. And you might say, what if I don't want to link? Well, then you just put a 0 in there. You write the link address to register 0. Right? That's another reason why we register 0. But anyway, yeah, so this is not for a jump instruction, actually, it's for jump and link. You guys with me? You guys know what you're writing with the jump and link? You're writing the next instruction after the jump, which is your return address. Right? So you jump somewhere and then you want to return to the caller, right?
Like function calls.
Right, it's for a function call, right. And the link address is not your standard 31 like we used in MIPS. Now you can put whatever you want there. Although I think the convention in RISC is 1. Register 1, I think, is a link address instead of 31. You might remember that from MIPS. So little different. And then there's a jump and link register. We also had this in MIPS. And this one has yet another addressing format. So this is the third way to address an instruction so far. This is different. So we've covered the B-type PC relative, we've covered the J-type PC relative, and now we have this other one, and this one is the most craziest one. This one, when you use jump and link, it reads a register. Read data 1, that's the contents of the RS1 register, and then you add the offset to it. And you put that in the program counter. So this is what I call the JALR address. So again, I give you the code for this. Now you'll see how all these fit in. This is not PC relative, by the way. This is relative to the register contents. Okay, so how does this all fit together? Well, I give you the code to generate the branch address, the JAL address, and the JALR address. And those three are then going to be fed into a MUX. This is a new MUX. You don't have this one. And this MUX will then be combined with the regular old PC+1 counter, and you select it using PC source. So PC source does two things. It determines whether you're going to just keep going, fetch the next instruction in the program, or if you're going to go somewhere else. And if you're going to go somewhere else, you also have to define where you want to go. It depends on what kind of branch or jump instruction. So all you got to do is set that to 0 if you just want to keep going. You set it to 1 if you are executing a branch and that branch should be taken. Or you set it to 2 if it's a JAL. And you set it to 3 if it's a JALR. Right? So your control unit simply has to set that based on what kind of instruction is in there. And if it's a branch, it additionally needs to know, it needs to resolve the branch too, to know if it's taken or not. Yes?
Here is delays, PCX, and stall execute.
This PCEX? Yeah, I mentioned this earlier. So this is literally just add a register to PC. The reason we have this is because, for 2 reasons. One, oh, well, wait a minute. Let me think about that. The one reason we have that is because the PC, the branches and the jumps are calculated with respect to that, right? They're calculated with respect to the instruction that's being executed, unlike MIPS, which uses the next instruction, right? I think I know why Hennessy and Patterson did that, because, or Patterson, I should say. I don't know if Hennessy was involved. Patterson chose that because I think there was 40 years of students in architecture classes being confused about that. Why do we calculate branches relative to the next instruction instead of the current instruction? It didn't make any sense. I think that's why they did that. But PCEX, I think that's it though. I think that's the only thing we use that for, because if you link, the value you put in the register file is actually PC fetch, because when you link, you want the next instruction, right? We want to go back to where, we don't want to, when we go to a function and come back, we don't want to come back to the jump that brought us to the function in the first place, right? We want to come back to where we would have been after the jump, right? Make sense? So when you write back, it's going to be PC fetch, not PCEX. So you have to be a little careful there. But all that stuff is in these diagrams that I show, assuming I don't have any bugs in here. Okay, I'm going to get to stall in a second here. Just
one other question.
Yeah.
What if we have on the PC fetch some instruction, and it's an execute state, but we shouldn't execute it because it's a branch instruction?
Right, that's what the stall is. Yeah, so I'm going to get to that. So the stall, so here's the problem. We've got this pipeline. And by the way, this is a classical problem in computer architecture. Unfortunately, there's no way to solve this completely. But every time you, if you have a pipeline CPU, and all modern CPUs are pipeline, every time you encounter a branch or a jump, by the time the CPU even recognizes what the hell it is, it's too late. You've already got the instructions starting from the next instruction have already been fetched and in the process of being executed, right? So if you have to then branch, you have to kill those instructions. You have to flush the pipeline. Well, not the whole pipeline, but only the things in the pipeline that were fetched after the branch, right? And that hurts you. That ends up inserting no ops into your pipeline, which don't do any useful work. So basically, what that means is that your CPU's performance suffers horribly whenever you have branches and jumps. So if you have a control-dependent code, like a graph algorithm that's trying to do a graph traversal, that performance is going to be lower than if you have, a more predictable type of code. Now, in reality, real processors have branch predictors that try to predict as early in the pipeline as possible where you're going to go, so it can minimize the amount of stalls. But in our CPU, we're just going to assume that when you have a branch, let's say you have an add branch, some instruction that comes after the branch, and then, well, hold on, let me start over here. So let's say we have 2 adds in a branch, right? So when we fetch the branch, we'll have the previous 2 instructions in the pipeline, right? And then when the branch moves to execute in the next cycle, the problem is that whatever instruction is in the code right after the branch is already being fetched at that time, right? So that's the problem. And if that branch, and the reason I have that T there is that means it's a branch and it's taken. It's a taken branch. So this next instruction is sometimes called the fall through, right, or the branch delay slot. It's the instruction right after the branch. So what we want to do is convert that instruction into a bubble, or a stall, or a no-op, same thing, right? when it passes from fetch into execute. So basically, what I'm saying is we're going to allow the next instruction to go through the pipeline. We don't have a choice. It's too late to do anything about it. But we're going to convert it into a bubble, a stall. Now, in the old day, now we have gone back and forth in this class as to how to actually implement this. In the old days, we used to put a mux in the fetch stage that would basically send in a no-op instead of the next instruction being fetched, right? The problem, though, is that was not workable. It wasn't a good solution because the instruction memory is a synchronous memory. Remember, we talked about synchronous RAM? So you can't put a mux after it's too late to do that, right? So the better way to do it is to basically fetch the instruction normally, just let it go. But have a 1-bit signal called stall that you assert in the execute stage. And when that stall, then you assert it in the execute stage, it goes to the fetch stage. And when that stall signal then moves into the execute stage, it'll move in there along with the instruction that was fetched. And it's just a disable flag. Basically says, you can't avoid it. You're going to fetch the next instruction, but the stall flag will tell the CPU not to write back the register, not to do anything, not to basically cripple the instruction, right? To render it, make it so it doesn't change anything, change the state. Okay?
Yeah, thank you.
Which means two things. One, it means that if the fall-through instruction was a branch or a jump, then obviously don't do it. Ignore what it tells you to do, right? And if it's like, say, an add instruction, you could do the add. You could let the ALU do the add, but don't write back the result, right? That's what the stall means, okay? So in your control unit, it's super easy to implement. You just have an if condition at the very beginning of your control unit and say, if stall underscore EX, then put all zeros out, right? Else, anything, then you can have an else that encapsulates the rest of your control logic, right? And so that's what the stall is, and I think this is the best way to do it. So the stall, now it's a little confusing though, because your control unit will have a new output called stall, and it will be connected to a signal called stall fetch. And you might be thinking, wait a second, every signal coming out of the control unit has an underscore EX after it, except for this one. This one has an underscore fetch. Why is that? Because it applies to the instruction being fetched, right? So you will still have a stall underscore EX, but it goes to a register and gets delayed, right? Now this is important because if you don't put this register here, if you have a feedback that goes from execute back into execute, or the control unit back into execute, which inevitably several groups will do this, they'll forget this register, and this will end up as a combinatorial loop, because what will happen is you'll see the branch and the control unit will say stall. But if there's no delay there, that stall comes back around and the control unit says, within the same cycle, it'll say, oh, it's a stall. Don't stall. And then it turns off the stall. And then when it turns off the stall, it realizes, oh, it's a branch, I have to stall. And then it sees the stall and says, oh, I don't need to stall, I'm stalling. So it turns it off, and it goes in an infinite loop. It's a combinatorial cycle that never ends. And that will actually lock up ModelSim, believe it or not. You'd think ModelSim would be able to detect a loop and just tell you that with an error message, but no. It just hangs, locks up. You'll run it, but the funny thing is it won't lock up immediately. It'll run fine until you hit a branch instruction, then boom, it locks. So you'll run ModelSim and you'll have a go. It'll hit the branch instruction, and you'll be 20,000 nanoseconds in and hang. And once that happens, it's hard to diagnose that. You have to kind of just comment out half your code and try again to try to whittle down where the loop is. Now this is the most common source of loops, so I'm telling you now, if you guys see that happen, you could probably go straight to the stall logic. Okay. All right, so here's the changes you need to make. You need to basically add the branch address, JAL address, and JLR address in your code. I give you the code for doing that. You just have to copy paste it in. Add the PC source to control the PC mux. The PC mux, you have to do that. Right? You have to add the PC mux, but that's just a ternary statement. You have to add the stall fetch as an output of the control unit. You have to add the stall EX as an input to the control unit. You have to, and then of course join them with a register. Add PCEX as a possible input to reg write. And then, you know, this is what I just explained. If stall is asserted, don't write. Yes. Oh, in the resolution. Yes, almost forgot. There's the branch resolution. I haven't addressed that yet. So, how do you know if a branch should be taken? Yeah, basically that's it. The ALU, if you guys remember, the ALU has an output called 0. You didn't use it yet. Now you're going to use it. 0 means that the output of the ALU operation is 0. So if you're testing for equality or non-equality, you basically just subtract your two inputs, and then if the output is 0, the 0 flag goes high, it means they're equal. Or alternatively, if it's low, that means they're not equal, right? There is a branch if less than.
Subtract.
Well, you could, but the ALU already has the functionality it is based on subtract. But if you use the SLT operation on the ALU, set less than, you can use that. So basically, this is really the hardest part of this is the branch resolution. Most of the other code we've given you. But for the branch resolution, you have to set, when the branch is in the execute stage, you have to treat it like an ALU operation. And then the ALU output has to come back into the control unit, right? So it feeds back. There's a possible loop there. You have to be careful because the ALU, the control unit's telling the ALU to do something, the ALU is going to do something, and then it's going to feed the output back to the control unit, which may impact what the control unit's doing. So you have a loop there. But if you design it carefully, it'll be stable, right? So I'll let you guys figure that out. I mean, to give you a hint, it's basically a nested if statement inside the control unit. That's the solution to the problem. But you have to just be careful with that, the way you write that. Okay, so yeah, and this table summarizes actually exactly what the various, there's 6 branch instructions. And this table, to give you some hints here, it tells you what the corresponding ALU op should be and what the logic is, right? So in other words, if you're doing branch if not equal, you set the ALU op to subtract, and then you branch if the R coming out of the ALU is not 0, right? Or you could just look at the 0 flag, as I mentioned, right? Okay, okay. So now I'm speeding up a little bit here because I want to get through all this. But if you have any questions, please don't hesitate to stop and ask. So this is a test program for the branches. This one's a little weird and complicated. So the idea with this is that we want to test all the branch and jumps at least once. And so this is kind of a little minefield. You have to, you start out and you're going to start branching all over the place, but there's a pattern that you have to look for. And so remember in the old test program, we gave you the answers, the register answers, but now the answers are not in registers. The answers are the fetch sequence, the sequence that it uses to get through this, the control sequence. So basically what you're looking for is, you're just looking at the program counter. So what you should see is it should go 0, 1, 2, 3, 4. 0, 1, 2, 3. So 0, 1, 2, 3. So 3, that's your first branch. And that's taken, evidently. Is that logic right? Branch if equal, 4, 5. Oh, they're not. Oh, sorry. Scratch that. Scratch that. Sorry. That branch is not taken. Obviously, -1 is not equal to 2. And so that's not taken. So we fetch 0, we fetch 1, we fetch 2. No problems. Nothing weird happens, right? Then we fetch 3, which is the 4th instruction, which is the second branch instruction. And this one says, is register 4 and 5 not equal? Yes, they are not equal. -1 is not equal to 2. So that should branch. Now here's where it gets a little weird. The problem is, again, is that when we execute that guy, we've already fetched the next instruction, which is 4. We've already got the next one. So that one is in the pipeline, can't stop it, but it's a stall, right? So you should see your stall signal go up there, right? But then the program counter will jump from 4 to 8. Right, now ideally it would have went from 3 to 8 because it would have fetched 3 and it would have went to 8, which is the target, right? Is that the target? It's target 3. Target 3 is here, which is 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, target 3 is 8. Oh yeah, and you can also look at, yeah, sorry. I have a column with the program counters here too. Okay, so ideally we would have grabbed 3 and went immediately to 8, but can't do it because of the pipeline. So, and by the way, if this was a 5-stage pipeline, you'd have had more than one stall in there, right? This is another reason why we did the 3-stage pipeline. Even with the 3-stage pipeline, you have to put a stall in, but if you had a deeper pipeline, you're looking at a lot more stalls in there. But luckily, it's just one stall. So you go 3, 4 is your stall, then you go to 8, and then 8 apparently is taken. Oh yeah, because there's a jump, it's unconditional. So we're going to jump back to 1, which is 4, right? So again, I'd like to go directly from 8 to 4, but I can't. I got to grab 9 first on the meantime, but it's stalled, right? Then I go to 4, and then I guess 4 is not taken. So, oh no, it is taken. Sorry, 4 is taken because then we grab 5, which is stalled. And then we go to 9. Apparently that's taken because when we grab 10, which is stalled. And then we go back to 9. I'm not sure how that works. I must, oh yeah, that's because of the jump and link. Yeah, that's the link stuff I'm doing there. But anyway, you get the idea, right? So again, this is a test program that you're looking at the sequence of program counters to know if you did it correct. So, before you're looking at the memory array, checking all the register values for the arithmetic being correct. Now it's just the control sequence. So that's the first test program. The second test program is going to be your calculator program. So this is basically the final project of the semester. So what we want to do is be able to put in on the board, on the DE2 board, punch an input value with your switches, like you guys have already done. So you've got 18 switches. So if that's an integer, that's a value from 0 to 2 to the 18th power minus 1, which is about 262,000, right? So our input is an integer. No fractional numbers, just an integer. But we want to calculate the square root of that integer, which then will be a fractional number, most likely, right? So we're going to calculate the square root, which you guys already wrote that code to do it. You're going to calculate it as having 14 fractional bits and 18 sorry, wrong. We want to store the solution with 24 fractional bits. Make sense? Now you might say, why 24? What is the deal with that? Okay, well the problem is we've got 8 hex displays to display the answer. So we want to show the answer as 3 whole number base 10 digits followed by 5 fractional digits. You might say, where'd you come up with those numbers? The 262,000 number that you would put in if you put all your switches up, you calculate the square root and it's 512. It's a 3-digit number. So when you go from binary to base 10, you want to be able to support up to 3 base 10 whole digits, and then the rest are fractional. The problem is that if you have 5 base 10 fractions, what is the precision of that? It's 10 to the negative 5th power, right? Which is 1/100,000th, right? 1 over 100,000, 1 over 10 to the 5th power. However, if you have 24 fractional bits, 2 to the 20, what's 1 over 2 to the 24th is 16 million, actually. So, right? Is that right? 16 million? Yeah, so we're good there, right? We actually would have more precision in here, right? And that leaves 32 minus 24 bits for the non-fractional part, right? Which is 6 plus 2 is 8 bits, right? Which is good. 8 bits will store 512, right? No, 8 bits is 256. Oh yeah, sorry, that's 20, that gives us, that would be 20, that would be 31, no, actually, that might be a typo there. 32, 24, that must be 20, this should be 23 actually, right? Because you need to have at least, we need to have enough bits to store the square root, the whole number part of the square root, which is 512, right? Which is going to be 9 bits, right? The number won't be 512, it'll be under 5, it'll be 511.999999, right? So it'll be 9 bits. So yeah, so that should be 23. Make sense? Sorry about that. Sorry about the typo. I don't know why that was in there. Okay, so makes sense? So how does that work though? How do you do the base 10 fixed point stuff? How's that work? Like you got to go from, you're going to have, like say your internal value is going to be 23 bits fractional, right? 9 bits non-fractional. But then how do we, you can't just, ideally you just run it through your base 10 conversion program, right? But that's not going to work. So how do you solve that? Well, the way you solve it is all you have to do is take the number that you calculate and just multiply it by 100,000. In binary, just multiply by the constant 100,000. That will effectively just take whatever the fractional number is in the binary, it'll multiply it by 100,000, so you'll basically move the base 10 decimal point 5 digits to the right. Okay, we'll have more details in the lab description. So basically what I'm trying to say is that this should not require much change in your square root code or your base 10 conversion code. The only thing you have to add is actually the multiply by 100,000, and everything else should fall into place. Okay. Yes, well, it's 23, so this gives you 8 million, 1 over 8 million precision, and that's fine because the base 10 is your granularity, your unit in the last place on the hex displays is 1/100,000th, right? So this will give you actually more than that, so that's fine. Yeah, so you should get the correct, ideally, your number on the hex display should be as close as you can possibly get with five fractional digits, right? So you have a calculator that can do a square root from switches to hex displays, right? Running on your CPU. Now you might say, well, wait a minute, why do we wait till now to do the square root code? Well, because your square root code is littered with branch instructions, right? So now that we have branch instructions, we can do it. Okay. And that's what I just got done explaining. Okay, yeah, so that's it. That's all there is to it. We will post a detailed lab sheet online for you guys. I think we pretty much have the rest of the semester budgeted towards this project. We'll put a due date on there, but I believe it'll be basically the end of the semester, right? If you're a grad student, though, you're going to have to work on the graduate lab as well, right? So you'll. Sorry? Lab 5 is taking this version of the CPU and executing 2 instructions in parallel. So fetching and executing 2 instructions at a time.
So making like 2 cores for you.
Well, basically, but we're using, it's called very long instruction word, VLIW. It's a VLIW instruction. Or you could call it superscalar. It's not exactly superscalar though, because you have to avoid, the compiler has to avoid putting 2 instructions together that don't work together. that would break the program if they're executed in parallel. So there is a little bit of instruction scheduling you have to do. So it's closer to a statically scheduled program. But you'd want to basically copy and paste some of the code from your CPU to support 2 simultaneous instructions, where one of them can be a bubble, a no-op if necessary, right? But ideally, at most, you can do 2 instructions, so this would, in theory, give you up to twice the performance by just replicating some code, right? That's the idea. But I have some slides where I'll go into detail on that.
But if 2 instructions are in conflict, we should stall one of lines.
Exactly, yeah. Which is going to be done at the compiler in the program. So you as a programmer will have to put the stall in there manually with a no-op. But you can do that. That's okay. So you'll lose some performance, but generally we want you to get about 30% more improvement. So 30% of the second slot should hopefully be not a no-op, right? But 70% can be no-ops. Okay, thank you.